theme. All right, so we talked about UDP. Now it is a good time to talk about TCP. So we will talk about segment structure, reliable data transfer, flow control, and connection management. So there are many RFCs defining TCP. Actually, now there are many different versions of TCP, like TCP Reno, TCP New Reno, and that kind of name. So actually, saying that TCP is only a single thing might not be ideal. I mean, the data structure of the TCP is valid for all of them, but how they work actually changes, because not RFCs. I mean, RFCs do not explain everything. Sometimes they leave some details to us. So how you apply them, changes how you're using the TCP. But more on that later. So it is point to point, one sender, one receiver. This is important. Actually, you cannot kind of use it like a broadcast. I mean, one sender and many receivers does not work in this scenario. This is why we have different applications for every connection. Reliable in-order byte stream, no message boundaries. Full duplex data, bidirectional data flow in same connection. MSS, maximum segment size. This means that if you have huge data, we will divide it into segments, and that size is actually variable, but there is an upper limit. Okay. There's also a nice way of attacking. You can, divide it into very small pieces and, send it in a very slow way, and this way you can keep the connection open. Cumulative acknowledgements, we will talk about this in a minute. Pipelining, TCP, congestion and flow control, set window size. Connection-oriented, handshaking, exchange of control messages, initializes sender-receiver state before data exchange. Flow-controlled, sender will not overwhelm receiver. So let's look at the TCP segment structure. Again, this is 32 bits. So we have 16-bit source port number and destination port number. We have sequestration number. This is segment sequestration number, counting bytes of data into byte stream, not segments. So, you might be sending 2 segments, but, they might be consist of 1,000 bytes. Here you are actually writing 0 or 1,000, determining to show which, byte that's actual sequence starts with. Okay. We will see an example in a minute anyway. Acknowledgement number, sequence number of next expected byte. Here, A bit is, saying that this is acknowledgement. There's an application data here. Again, as I said, this is variable length. Data sent by application into TCP circuit, but of course, there is an upper bound, which I said MSS. Internet checksum is here. We already talk about it when we talk about UDP. TCP options here. Again, this is variable length, and you can write many different things here. Here you write length of the TCP header. You have some flags here. This is for reset, SYN, FIN, connection management. FIN actually to enter connection and so on. Receive window. This actually, allows flow control, number of bytes receiver willing to accept. Here you have CNE, congestion notifications. There are some other fields which generally never used. Okay, but you for urgent saying that this segment is urgent, that's all. All right, so sequence numbers, byte stream number of first byte in segment data. Here you have sender sequence number. Here send ACKS, and so on. This picture actually shows you the window size. So outgoing segment from sender, you write the sequence number here. Acknowledgements, sequence number of the next byte expected from other side, and you have, if you receive more segments, you actually say it in a cumulative way. Question here is how receiver handles out of order segments. Answer is TCP specification doesn't say, up to the implementer. Actually, I'm moving from the slides in a fast way because these examples actually shows us what to do in many scenarios. So there are some simple scenarios. Here they're assuming that we are using Telnet, which actually doesn't provide encryption, so it is not secure, and you should use something like SSH in practice. But assume that host A sends, for instance, in your keyboard. Actually, this is what some people don't know. If you use Telnet, when you write something on your keyboard, sometimes it appears in a, with a delay on your screen. This actually means that when you type C, you send it to the host, the server, it receives it and sends you that, says that it received it, and then it appears on your screen. This is the slowdown, actually, okay? So assume that there is a handshake happened before here, and this way now they are starting sending data. So currently assume that host A is at the sequence 42, and from host B, he received many data before, so acknowledgement is 79. This means that I received 78 bytes before. Now I'm waiting for the 79. Of course, host B may not send anything. You're just saying that you're ready to receive this sequence number, right? So your data is now C. In your keyboard, you press C on your client. So server receives this and echoes it back. So here, as you can see, now the data host sends is this acknowledgement number, actually. And host saying that I received sequence 42. Now I'm ready to receive 43. And sends the data C back. Now you receive the C also. This is what you show it on your screen. Now you don't have anything to send, but you're just sending acknowledgement of the data you received here. Okay. Now you are ready to receive 80. This is why you're always writing here one more than what you received so far. Okay. So this is why it increases by 1. How to set TCP timeout value longer than RTT, but RTT varies. If you make it too short, premature timeout and unnecessary transmissions. If it is too long, slow reaction to segment loss. Okay. How to estimate RTT? Sample RTT, measure time from segment transmission until ACK received, ignore retransmission. Sample RTT will vary. Want estimated RTT smoother. Average several recent measurements, not just current sample RTT. So here's what I'm trying to tell you. So here's a formula. Here alpha is a variable, and we will choose it like 0.85 in a second. So here, yeah, it's typically this. So when you subtract it from 1, it will mean something, 0.875. So this is for exponential weighted moving average. So this means that you are measuring the RTT constantly, but estimated RTT is multiplied with this number. So this means that if you started to get slower RTTs, it will affect this way. So this is why it is called exponential weighted average. Weighted means you are choosing this value like this. Okay, so there are some averages here, estimated RTT and sample RTT as follows. Here, the RTT is increased. Timeout interval, estimated RTT plus safety margin, large variation in estimated RTT, want a larger safety margin. So generally what you do is as follows. You start with an estimated RTT, and if you start transmission losses, you double your estimated RTT, so you double the timeout interval so that you wait more until the connection goes back to normal. Yeah, there are some therefore the deviation. Okay, I'm not going into detail because in network courses these are the nice homework and exam questions. All right, so but I'm not going to give an homework about it, so I'm moving on to more definitions and actually more scenarios and what happens. Event is data received from application. So TCP Sender simplified is as follows. Create segment with sequence number. Seg number is byte stream number of first data byte in segment. Start timer if not already running. Okay. Think of timer as for oldest unacked segment. Expiration interval, timeout interval. Okay. Event timeout, retransmit segment that caused timeout, restart timer, event ACK received, if ACK acknowledges previously unacked segments, update what is known to be ACKed, start timer if there are still unacked segments. Okay. So event at receiver, arrival of in-order segment with expected sequence number, all data up to expected sequence already ACKed, TCP receiver action, delayed ACK, wait up to 500 milliseconds, for example, for next segment. If no segment is received, then you send ACK. Arrival of in-order segment with expected sequence number, one other segment has ACK pending, immediately send single cumulative ACK in both in-order segments. Arrival of out-of-order segment higher than expected ACK, gap detected, immediately send duplicate ACK indicating sequence number of next expected byte. Arrival of segment that partially or completely fills gap, immediately send ACK provided that segment starts at lower end of gap. All right, so these might, actually try to show you how it works. So it will be more clear when we look at the retransmission scenarios and what happens during the loss. So here, let's look at the example from the book. So host A sends this data, its sequence number 92, and sends 8 bytes of data. So this means that I will send ACK 100 to show that next sequence will start with this. But for some reason, this data packet is lost, right? Since host A never received ACK, but he does that, wait for timeout, timeout occurs and sends the same data. So host B receives the same data. So if they already received, they don't bother to, record it again. They just drop this packet, but send the ACK again. So the main actually loss ACK scenario happens like this most of the time. Okay. Second scenario, premature timeout. So what happens is as follows: you send two packets, sequence 92 of 8 bytes and sequence 100 of 20 bytes of data. So when you receive them, host B actually sends ACK 100 for this, then ACK 120 for this. Okay. But the problem is that if your timeout interval is short, and you time out the connection before you receive the ACKs, then you receive this X. So you send the sequence 92 again, and this sends cumulative ACK for 120 because this says that instead of sending ACK 100, if the host B already stored this data, you can send cumulative ACK. But this is actually, an implementation thing. Maybe, some of them, host B might drop all of this data if they detect that the communication is lost and, restart and so on. But this is generally what happens. This is what we meant by cumulative ACK. Instead of sending ACK 100, you say ACK 120 because saying this actually doesn't make sense. You already received that data. Okay. Cumulative ACK covers for earlier lost ACK. Here, let's look at the example. So you again receive the same sequences, and you send ACK for 100 and 120, but this data packet is lost. But this doesn't mean anything for host A because when they receive this means that until this part is everything is okay. So they start sending the next one. TCP fast retransmit example. So you send many data in this example, like 5. So you send ACK for all of them except this lost data packet. Okay. So in all of your ACK data, since you never received this, you are sending 100. So during the timeout, host A received many times that the same ACK. So receipt of 3 duplicate ACKs indicates 3 segments received after a missing segment. Lost segment is likely, so retransmit. Right. So before the timeout, host A resubmits it. This is the good thing about TCP. So TCP fast transmit, if sender receives 3 additional ACKs for data, triple duplicate ACKs, resend unacked segment with small segment number, likely that unacked segment loss, so don't wait for timeout. That is the idea. Okay. Flow control and connection management. In the flow control, what we have is as follows. Network layer delivering IP datagram payload into TCP socket buffers. This is the receiver protocol stack. Application removing data from TCP socket buffers and writing it to application. So here you have two data. That is data that you received and data you have read actually, right? There's difference. So what happens in network layers delivers data faster than application layer removes data from the socket buffers, right? So you're receiving in a very fast way, but application receives it in a slower way. So this is actually what they talk about flow control. Okay, this is why we have receive window part here. This part actually number of bytes receiver willing to accept. Actually, this is just a simple subtraction operation showing that currently what data you received and which of them you read. Okay. Flow control, receiver controls sender, so sender won't overflow receiver's buffer by transmitting too much, too fast. TCP receiver advertises free buffer space in, this R window field in TCP header. And receive buffer size set via socket options. Typically, default values 4096 bytes. Many operating systems auto-adjust this buffer. Sender limits amount of unacked in-flight data to received, like this. Guarantees received buffer will not overflow. Okay. So this is your free buffer space, and this is what we say by this variable. Okay. So this is the number of bytes actually the receiver willing to accept, right? So TCP connection management is as follows. Before exchanging data, sender receiver handshake, agree to establish connection, each knowing the other willing to establish connection, agree on connection parameters, for example, start and sequence numbers. So everything is already, recorded in this part. So this part is trying to tell us why two-way handshake would not work. For instance, in the two-way handshake happens like this. So you say, let's talk, and the person acknowledges it. But now, this person doesn't know that this person received this acknowledgement. So this is why we actually do the three-way handshake. So at this point, when this person requests, X, value X, so like it is requesting this value and this sending it. Question is, will two-way handshake always work in network? The answer is, you might guess no, because we already talked about we will have three-way handshake. So because there will be variable delays, retransmitted messages due to message loss, message reordering will be a problem and can't see other sites. Okay. So here are some two-way handshake scenarios where things doesn't work. Like in this case, you request X, they send you X, now you send data X plus 1, they accept it, so connection is completes here. But in practice, this may not be the case, right? Connection completes here, client terminates, server forgets X, now you retransmit X, you again establish the connection. So this causes half open connection, no client. And here are other scenarios, after the timeout and so on. I'm not going too much into detail. Here you are sending the same data again, so duplicate data accepted. So instead, let's look at the TCP three-way handshake to overcome all of these problems. So in three-way handshake, what happens is as follows. So client sends SYN bit equals to 1. Recall that in the TCP headers, we have a flag as SYN. And you write the sequence. And this is actually generally, if you're starting the connection, randomly selected, okay? So actually, you should have a nice random number generator here. Because if you use always, for instance, start with 0 or so on, if you connect it to that server again and, terminate the connection, and when you reconnect with this similar sequence numbers, this might cause some problems. This is why they don't want to store all of these sequence numbers. Instead, when the connection ends, they remove it from the memory. So this is why in each connection, you choose it in a random way. Your starting point is randomly chosen, okay? So choose init sequence number, X sends TCP SYN message. So choose init sequence number Y. Again, this is randomly created for the server. X is for the client. Now you send TCP Sender message, ACKing SYN. So you create ACK bits equals to 1. These are important because in the firewalls, this is one of the ways you can create rules. This way you can block anything if you want. For instance, if you want people to create, three-way handshake, you can block requests that have SYN bit equals to 1, for instance. A simple rule to block many connections. So receive SYN ACK indicates server is live. Send ACK for SYN ACK. This segment may contain client to server data, right? So when the server receives this indicates that client is live. From this point on, now you are synchronized, with the values X and Y. And this way we can, do all of the things that I already mentioned in the previous slides. So the book says, creates a human analog in this way. So you are climbing, you are asking is on belay. The answer is belay on. Now you say that climbing. So this is in TCP what happens. You realize that everybody is online. Now you're starting actually sending the data. Okay. So how we close a TCP connection? Client, server, each close their side of connection. So both of them has to end. So you send TCP segment with FIN bit equals to 1. You respond the received FIN with ACK. On receiving FIN, ACK can be combined with your own FIN. Simultaneous fixed exchanges can be handled. Okay, so this way you end the communication. So this concludes our, discussion of TCP.